Yeah, good afternoon, folks. My name's Natalie Curran. It's good to be here talking all things SPA and Artemis. So I'm going to be providing an overview of the SPA basin and specifically methods used to constrain the age. So, next slide, please. Awesome. So I know this has already been highlighted a fair bit today, but I wouldn't be doing my due diligence if I didn't double down on everything that was said. So, and why the SPA age is so important. For the last several decades, figuring out the chronology of the moon and one of its largest anchor points being the age of SPA has been pretty much number one priority for most, if not all, community planetary and lunar science documents. So it's a very critical piece of information we need to assess the bombardment history, not just to understand the moon, but to connect it to the wider solar system, including our own Earth, and potentially an era that may have affected the rise of habitability here on Earth. So not to mention this beautiful region is scientifically rich with these so many amazing basins and craters that are shown in this image here, which is from the Endurance mission concept. I love this image. It just shows you the complexity of the SPA region. But next slide, please. So I figured I would start off with a good overview of the current predictions, estimates, and measurements of ages that surround SPA. We have quite a lot of uncertainty in this age right now. Age estimates go from, about 4 to 4.4 billion years, and they're from dynamical modeling, crater counting, stratigraphy, and also samples. Until recently, we didn't have any direct sampling from the SPA region. We do now. We have some Chang'e 6 samples. So I'll go into a little bit more detail on each of these areas next. So if next slide, please. So first off, dynamical models. So age constraints in the world of modeling are done using things like crater counting models, Monte Carlo simulations, as well as geochemical data from lunar samples in the form of highly siderophile elements. So we've all seen this graph. Well, I'm sure we've all seen some form of this graph. We had it in Brad's slides as well. But we're trying to constrain, especially the early portion of this type of graph with anchoring that SPA age. Now, dynamical models recently have, especially those by the authors that are listed on the bottom of this slide here, have given us basically a new tool to estimate the age of SPA indirectly without the samples. So these models simulate the cratering record by tracking things like planetesimals from terrestrial planet formation and using simulation techniques to statistically reproduce large impact basins on the moon. So these are calibrated against lunar sample data, particularly the abundance of HSEs, which are key traces of late accretion, but I'll go into that in the next slide. So based on this semi-recent modeling work, the SPA basin most likely formed between about 4.3 and 4.4 billion years ago. So not immediately after the moon formation, but also predating basins like Nectaris and Imbrium, given the ages that we have by, several hundred millions of years. So one key constraint is for these modeling is the number of superposed large craters. So those with diameters above 150 kilometers on top of SPA, which tells us, that they must be that SPA must be older than most of the major basins that we can. I'll use this lightly, but that we can date more confidently. Although there are still some issues. Next slide, please. So what does it mean if SPA formed as early as 4.3, 4.4 billion years ago? So many of us in the community, and I realize I'm using my mouse, but you can't see me pointing, but imagine I'm pointing at this graph to the right, shows us the impact flux through time on the moon, whether we see a spike at 3.9, whether this was gradual, whether this was like a sawtooth, things like that. A lot of modeling work has gone into this. And these recent models have support the idea that the moon actually experienced a steady decline in impacts. So like the tail end of accretion, rather than this sharp 3.9 billion year like late heavy bombardment spike at 3.9. So in this view, SPA, Nectaris, and Imbrium simply just mark a progressively younger impacts along the long line of decline. So that makes SPA a key anchor point for understanding how quickly the solar system settled down after planet formation. It's one of the reasons why we really want an age for this. Next slide, please. Yeah, awesome. So another important line of evidence, as I mentioned, does come from geochemistry of lunar samples, specifically the HSEs. These elements are generally strongly preferred to go into metal. So during core formation, they should have been completely stripped from the mantle. But we still find small amounts of HSEs in lunar rocks today. So this tells us that elements were later delivered by impacts after the moon's core had already formed. So now here's the interesting bit: dynamical models of declining impact flux, meaning that impacts early, then they tapered off, predict that a small but measurable amount of chondritic material should have been added to the moon over time. And that's exactly what we see. So these HSEs in lunar samples match what those predict for like declining flux models. So you can see here in red, we've got this kind of like sawtooth rather than a peak at that 3.9 billion years. And if there had been a massive spike in bombardment, we actually like something like the late heavy bombardment, we'd expect to see far more HSEs than we actually do. So the geochemistry supports a more gradual decline in impacts, and by extension kind of suggests that SPA likely formed early during the declining phase. The decline during the final stages of this tail. So next slide, please. So moving on to a different method or technique of calculating the age, we have geologic and geophysical constraints. While dynamical models suggest SPA formed as early as 4.3, 4.4, we can also get a lower limit or minimum age using geological and geophysical observations. So first here, I have a detailed crater mapping by Ivanov and others that show the younger craters superposed on SPA formed no earlier than 3.98 billion years. So given the laws of superposition, that SPA must be older than this. Next slide, please. Secondly, we have lunar magnetic anomalies. So these anomalies are remnant magnetizations. Essentially, they're frozen in time magnetic signatures that are preserved in the crust from when the moon's dynamo was active. These magnetic anomalies in the basin, which shown here, this is a map mapped by Proker et al., are mostly concentrated in the 3.6 to 3.8 billion year range. Excuse me. Since large impacts, especially such as SPA, would kind of reset this magnetization, these anomalies likely formed during or shortly after SPA. So again, together these don't provide an exact age for SPA, but they give us a minimum age window for when the basin could have formed. So before 3.9 and likely closer to 4.1, in a bit more of an agreement with dynamical models. Next slide, please. So I mentioned that recently we've got back direct samples from the SPA region. So Changi 6 brought back nearly 2 kilograms of lunar soil from the Apollo Basin, which is within SPA. Researchers have analysed about 1,600 fragments, and they identified about 20 noritic clasts, which you can see a picture of an image of one of those clasts in the top right here. And the texture and chemistry of these clasts show that they came from an impact melt sheet. So it had to be a big enough impact or major impact event to generate these type of samples. Also dating, lead dating of zirconium bearing phases revealed 2 distinct age ranges. So we've got one at 4.25 and one at 3.87. The 4.25 is what the author suggests records the original formation of SPA, while the younger one reflects a later impact, possibly related to something during the LHB. I want to stress this is really important samples and information, because it's the first direct sample-based age we have that comes from within the SPA basin. I mean direct by it was collected and brought back from that region. So it really does give us a solid anchor for refining lunar cratering chronology and understanding the early bombardment history from that area. Next slide, please. I know Brad just briefly mentioned this as well, but another important constraint comes from lunar meteorites. This is Northwest Africa 2995, which was investigated by Katie Joy and colleagues. And the radiometric, first off, it's linked based off the chemistry of the sample. So hopefully you can just about see it, but on the bottom right image of the moon, you've got little red blobs. They are regions that give the highest probability of where this sample comes from. And radiometric dating of different components within this meteorite yield very consistent ages of about 4.32 to 4.33, which the authors interpret as SPA basin formation age. So if this is the age, this means that SPA impact occurred around 120 million years earlier than the main cluster of other large basins, which is similar to what's provided ages given by modeling and things. These findings also challenge the idea of a tightly clustered LHB and instead support a more extended period of basin formation. Next slide, please. So back to our summary of ages, the samples are really helping to narrow this down, but much like, press next one more time, please. Much like the graph that I have to the side, which represents Apollo and meteorite impactites and their ages, this campaign to figure out SPA age is going to be more of a statistical task in getting samples and figuring out what the overlying, in quotation, younger basins are and crater ejecta versus this older SPA age, which hopefully should fall out from like targeting histograms of a statistical framework that we should be addressing with the next mission. So next slide, please. So how can Artemis 4 help with this whole narrowing down of age? So first off, Artemis 4 will provide an incredible opportunity to better define the age of SPA. This mission is planned to land within or near the extended SPA ejective zone, which means we'll have direct access to basin-derived material. The landing site is especially valuable because it includes a mix of pre-Nectarian and Nectarian age craters and basins, which will be very handy to understand their ages as well. That gives us the ability to build this really strong regional stratigraphy. So the key in this will be to systematically sample across different geological units. That means collecting impact melt rocks, breccias from overlying basins and crustal lithologies, where we can basically apply multiple chronometers to these samples to build this robust statistical framework. So SPH, I would hope, would be great if SPA could come from a single rock, but in the highly unlikely event that will happen, it will emerge from patterns in histogram peaks across many detailed clasts. So this approach gives us the best chance of tightly constraining when the basin actually formed. So I'll just go to my last slide and quickly wrap it up. So I just want to conclude that, the SPA age is still uncertain, somewhere between 4 and 4.4 billion years. To really answer this question, it's going to take detailed modeling, careful surface science, and dating of hundreds of samples using multiple chronometers. Chang'e 6 has really provided this useful constraint, but ultimately sampling with Artemis is going to be really critical to nailing down this age. And this matters because, SBA Basin isn't just another crater, it's the cornerstone of our solar system chronology. If we can date SBA precisely, it will anchor our entire timeline of planetary bombardment. So sorry I went a little bit over there. Thank you.